Hello, my name is Jared Ibarra, and this is my Lab 2 on projectile motion. This is my table of contents, and the goal of this experiment was to observe the motion of an object in both the x and y directions when it's thrown as a projectile over a time interval, and then use a Python model to analyze it. The only forces acting on the object were gravity and drag, and it started from an initial position of 1.10 meters with a initial velocity of 0.6 meters per second. This experiment relied on Newton's second law and the principle of momentum, and using these, we derived the velocity and position update formulas, which allowed us to predict the object's motion. And then we also used the gravitational and drag force equations to refine our model. To analyze the data, we use GlowScript and /webvpython to simulate motion, and we use Tracker to track real-world motion from a recorded video. And these tools helped us compare theoretical and experimental results. Our system was a crumpled paper ball with a mass of 0.003 kilograms and a diameter of 0.05 meters. We then recorded its motion and then ran two simulations, one considering only gravity and the other including drag, and then we compared their velocity trends. And this is my video. And these were my initial conditions with drag. As you see, the b equals 0.00009, and this is my initial conditions without drag, which the b just equals 0. And this is the loop that we used for both the drag and no drag. And the Python models generated data that we plotted for comparison. The gravity-only model showed continuous acceleration, whereas the drag-included model demonstrated terminal velocity. Our real-world data align more closely with the drag-included simulation. Potential sources of error included air disturbances, inaccuracies in the drag coefficient, human error in initial velocity, and calibration issues in the motion tracking, and these factors all could have hindered our results. For the what if, I answered if the object had been thrown upward instead of dropped, it would have taken longer to reach the ground. The total time would be 2 multiplied by v initial all over g, as it must first decelerate before reversing direction. And finally, for my what does it mean, the terminal velocity occurs when drag balances out with gravity, stopping further acceleration. And in a gravity-only model, velocity is kept increasing since there's no terminal velocity. And in a drag-included model, velocity levels off because terminal velocity is reached. And to observe it better, we could drop the object from a greater height or use a denser medium. And this experiment overall highlights how drag limits free fall speed in a real-world motion. For conclusion, this experiment validates the fundamental physics principles and demonstrated how computational models help analyze motion. Thank you for your time.